Welcome back viewers. So, now start with the lecture 5. So, this is in the continuation of the previous lecture. Now, in the previous lecture I have defined what is the linear differential operator. So, FD I have defined. Now, suppose my FD is simply a D. Suppose I have a differential equation like y dash x is equal to sin x. So, in this case I can write this differential equation as d of yx is equal to sin x. And if I want to solve this one, from here I can define my yx as d inverse into sin x. Now, d is a differential operator and that I know that my d is d by dx. So, what is the inverse of a differential operator? And that is the integration I know. So, from here I will get that d inverse will be integration of sin x with respect to x, and that my yx will be the solution of this differential equation. So, similarly my FD, now I have defined my FD. So, if you see that if my FD is a d square plus b d plus c, now this is my differential operator. Just I will differential operator. Now, what will happen if I want to define the inverse of this one? So, this is the differential operator and this is we generally call is integral operator. Because we know that the integration is also sometimes called the antiderivative. So, if the differential operator we are taking is this one, then the inverse of the differential equation we call it the integral operator. Now, the question comes that how to find the FD inverse for any differential operator. If it is a simple one, then we have defined that this is the inverse, but what will happen if I have my FD of this type? So, let us do this one for case to case, that how I will define this one. So, I will start with the case 1, number 1, when my function on the right hand side f x is some exponential function e alpha x. So, this is my exponential function, because if you see that in the previous lecture the equation number 2 I have defined this equation a y double dash plus b y dash plus c y is equal to f x, and I want to solve this differential equation. Then we have defined that this has a solution ycx plus ypx. Ycx is a solution corresponding to the homogeneous part, putting f x equal to 0, and then we define the particular solution, and to find the particular solution I have defined that what is the differential operator, and then we are going to deal with the operator methods to find out the particular solution. So, in this case I am defining the case number 1 when my f x is equal to e raised to power alpha x. Now, in this case what we will do is that I just want to find out that what will happen if I take d of f x. So, d of f x if I do, it will be alpha e raised to power alpha x. Now, I want to define what is the d square f x in this case. So, it will be alpha square e raised to power alpha x. So, from here what I do is that I take f d, so this is my differential operator, into e raised to power alpha x. So, from here my f d is already known that this is equal to b d plus c e raised to power alpha x. So, this is already known to me. Now, I put this operate this operator on the exponential function. So, I will get a d square e raised to power alpha x plus b d e raised to power alpha x plus c e raised to power alpha x. I can operate because this is a linear operator I can operate this function. So, after doing this one I will get a, and d square e raised to power alpha x is this one. So, it becomes alpha square e raised to power alpha x plus b, this becomes alpha e raised to power alpha x b alpha e raised to power alpha x plus c e raised to power alpha x. So, from here I can take e raised to power alpha x common from this. So, I get a plus alpha square b alpha plus c e raised to power alpha x. Now, what is this? It is similar to the my f d here, only thing is that instead of d I have changed my alpha. So, I can write this as a f of alpha e raised to power alpha x. So, from here I will get that my f d e raised to power alpha x becomes f of alpha e raised to power alpha x. Now, in this case what I assume is that my f of alpha is not equal to 0, because it may happen that when I put alpha instead of d, then this becomes 0. So, I am assuming that my f alpha is not equal to 0. Now, so I want to solve my differential equation. So, this is my differential equation and I want to find my particular solution. As I told you that the particular solution in this case will be f of d inverse e raised to power alpha x, where alpha f x is e raised to power alpha x. Now, from the previous slides I know that I get e of f d e raised to power alpha x is equal to f of alpha e raised to power alpha x. So, from here I can define that e raised to power alpha x, and I am taking the f d inverse both side. So, I will get f of d inverse f of alpha e raised to power alpha x. So, from here I can define that this e alpha x becomes, now this f alpha is a constant, it is just a scalar value, it is a constant value. So, if I am operating a linear operator on a constant, I can take this constant outside. So, it becomes f of alpha f of d inverse e of alpha x. So, from here I can write that 1 of f alpha e raised to power alpha x can be written as f d inverse e raised to power alpha x. So, from here now I am going back to here. So, from here I can write that f d inverse e raised to power alpha x can be written as 1 over f alpha e raised to power alpha x. So, from here now I can say that my y p x in this case will be 1 over f of alpha e raised to power alpha x. So, what do we do in this case now? That whatever the power e raised to power alpha x is there, put the value of alpha in the linear operator, and we are assuming that f alpha is not equal to 0. So, this is my condition that f alpha is not equal to 0, then this will be my particular solution. So, for example, so let us take one example. Instead of example, I will take both the cases. I will take the another case 2 together, that f of alpha is equal to 0. What will happen? Because in this case I have assumed that f alpha is not equal to 0, but now I have f alpha equal to 0. So, in that case I cannot divide by f alpha because this is already 0. So, to deal with this one, before dealing with this one, what I want to define is that some important results I want to define. So, some important results. So, what is that? I want to define that my f of d, whatever the differential operator we have defined, if I operate this on some function e alpha x into some function g x, then this can be written as e raised to power alpha x f of d plus alpha into gx. So, this is my results, and suppose I want to verify this one. So, I want to verify. Now, for this one what I do is that let us take the derivative of e raised to power alpha x gx. So, if I take this one, I apply the product rule for the derivatives. So, I can write it there the derivative of the first function. So, alpha e raised to power alpha x and then into gx plus e raised to power alpha x and g dash x. This can be written again as, I can write this way as alpha e raised to power alpha x gx plus e raised to power alpha x, and this is the d gx, which can further be written as, now what I do is that I take this d here, that is the derivative operating on the function gx. So, I can take from here e alpha x, I can take common on the left side. So, inside I will get d, this d plus this alpha. So, this will be alpha into gx. Now, if we expand this one, we will get, now this is a derivative plus some constant. So, if it is operating on the gx, so it will be first derivative of gx, so it will be e raised to power alpha x g dash x plus e raised to power alpha x alpha gx. So, you will get this value. So, this can be written as this one. Similarly, I can define this one for what will happen if I take d square of e raised to power alpha x gx. So, in this case I will operate on this one. So, I will get this value, this way I am writing here g dash x plus alpha e alpha x gx. This is a one derivative I applied. Now, I am applying the derivative again. So, again e alpha x alpha g dash x plus e raised to power alpha x g double dash x plus, so now operating on this one. So, it will be alpha e alpha x gx plus e raised to power alpha x g dash x, which can further be written as so this one can be written as d square e alpha x gx can be written as, now from here I collect the terms. So, this can be written as e alpha x g dash x plus, from here alpha square e raised to power alpha x gx, this can be taken as here, and this term together. So, it is can be written as 2 times alpha e raised to power alpha x g dash x. So, this can be written as like this. Now, from here what I do is that I take e f x common, and from inside what I do, I take d square from here, and then from here I take alpha square from here plus 2 times alpha d, I can write like this one, and I operate this one on gx, because if you take this one operating this function on gx, it will be second derivative from here, alpha square gx is same and 2 alpha dx. So, from here I will get E alpha x d plus alpha whole square operating on the function gx. So, from here what I see is that from I can write this function as my d square. So, d square E alpha x g x can be written as E alpha x d plus alpha square g x. Now, like this one, if I keep going like this one, then you will see that now I have my f d. So, I want to apply the f d on the e raised to power alpha x g x. So, I want to see that what will happen. My f d is a d square plus b d plus c applying on e alpha x g x. Now, this is the operator I am applying on the equation, applying on this function. So, this can be written as a d square e alpha x g x plus b d I am applying on e alpha x g x plus c e raised to power alpha x g x. So, this one, and from here I know that it can be written d square, I just written that. So, it can be written as e alpha x d plus alpha whole square g x plus b e raised to power alpha x. So, this I have taken, and this can be written as d plus alpha g x plus c times e alpha x g x. This further I can write this as alpha. So, what I do is now e raised to power alpha x I take the common. So, from here e raised to power alpha x I just take the common. So, inside I will get a d plus alpha whole square plus b d plus alpha plus c operating on the function g x. So, this is what? This is can be written as e raised to power alpha x, and this if you see instead of f d I have put d plus alpha. So, it will be d plus alpha operating on the function g x. So, from here what I will get is that f d e alpha x g x can be written as e alpha x f of d plus f g x. So, this terminology we can keep in our mind. Now, so I will use this one to study. Now, we want to study the case when f of alpha is equal to 0 in the, because when the f of alpha equal to 0 I can apply my case whatever the case we have just studied. So, in this case, so now see that f of alpha is equal to 0, which implies that my f d would be of the form d minus alpha into some function, I call it g d, because in this case we are dealing with this quadratic, or it may happen that f dash alpha is also 0. So, if f dash alpha is also 0, so in that case you will see my f d will be d minus alpha ki power square. So, if my f alpha is 0, then definitely by the knowledge of the polynomials we know that d minus alpha be one of the factor of the fd, and in this case my g of alpha is not equal to 0, because only f alpha is 0. But what happens that f alpha is 0 and then I take the derivative and f dash alpha is also 0. So, in that case this is the possibility. So, now if this is the happening, then suppose let f d is equal to this, then what is my purpose? I want to find my particular solution, and the particular solution I know that is inverse of e raised to power alpha x. So, that is my purpose. Now, my f d will be this one. Suppose I take this factor that f alpha is 0 and f dash alpha is not equal to 0. So, let this is the case. So, in this case I will take that d minus alpha g of d and taking the inverse e raised to power alpha x. So, this is the inverse. Now, so in this case also now this is the inverse. So, I can separate e raised to power alpha x. From here I can write d minus alpha inverse, and then this is the operator inverse e raised to power alpha x. Now, e raised to power g of alpha is not equal to 0. So, by the previous case I know that I can write this one as y, I can write this as y p x is equal to d minus alpha inverse, and then this one I can write from the previous one can be written as g of alpha e raised to power alpha x. And now g of alpha is a scalar, is a constant term. So, I can take as a g of alpha and then d minus alpha inverse e raised to power alpha x. So, this one is now, just now we have from the previous one we have seen that this can be written as g of alpha will be here. Now, I can take this function as multiply into 1, because now I am going to use that e of alpha x into g x, and g x in this case I am taking 1. Now, I can write this as, so I taking the e alpha x on the left hand side, and then it becomes g minus alpha plus alpha inverse into 1, just by the previous value we have defined here from here. Now, this can be written as, so this will cancel out. From here I can define, so it becomes e alpha x over g of alpha into d of inverse operating on 1. And what is this d inverse? It is just the integration. So, from here e of alpha x over g of alpha integration of 1 with respect to x, and this will be x. So, it will be e alpha x over g alpha x. So, that will be the particular solution in the case when f of alpha is 0. So, from here I can say that my y p x will be e raised to power alpha x by g alpha x. So, this is the case 1. Now, what will happen if in that case, suppose I have my f d is d minus alpha whole square. So, in that case what is happening, that f of alpha is 0 and f dash alpha is also 0. So, both the cases are happening now. So, in this case what will happen if I want to find my particular solution. So, this will be again my f of d inverse and e raised to power alpha x. Now, this is again d minus alpha whole square minus e raised to power alpha x. Now, I will apply the shifting operator and into 1. So, this one is there. So, this one I can write as e alpha x. Now, I am using the previous form. So, it becomes d minus alpha plus alpha square minus 1 into 1. So, this is the operator operating on 1 only. So, it will be e alpha x and this will be d, because this and this will cancel out operating on 1. So, if you see it, this becomes d inverse operating on 1. So, e alpha x, and what is this? It is the 2 time derivative or integration of 1 with respect to x. So, this can be written as e alpha x and this is the 2 time derivative integration I am taking. So, 1 is x square by 2 plus c x, this is taken, because if I do the one time integration it will be x plus some constant. So, in that case I take that constant as 0 and then again. So, in this case if you see this c I choose equal to 0. So, it will get, I will get only e alpha x square by 2. So, that will be the solution, particular solution when this is happening, that the f alpha is 0 and f dash alpha is 0. So, you can see from here that when the f alpha is 0 only, then this will happen, and when f of alpha and its derivative 0, then this will happen. So, this is the solution. Now, let us do one example on based on this one. So, let us take one example. So, example, I have a differential equation y double dash plus y dash minus 6y is equal to 5 e raised to power minus 3x. So, this is the non-homogeneous linear second order differential equation with my function f x I am taking on the right hand side is e raised to power minus 3x. And I know that this equation has general solution. So, that will be y c x plus y p x, where y c x is a solution corresponding to homogeneous part. So, from that one I know that if I solve this one, so from here I can find out that when I solve 6y equal to 0, six y equal to 0, then I will get my solution. So, this is lambda square, the characteristic equation will be lambda square plus lambda minus 6, that is equal to 0 and from here I can find out the solution. So, this is the way we can find out the roots of this quadratic equation. So, from here I will get minus 1 b square will be 1 minus 4 ac. So, 4 ac, so it is 24 by 2a. So, this is a 2. So, from here minus 1 plus minus it is 25. So, it will be 5 by 2. So, from here I will get two roots are real and distinct. So, from this one my lambda 1 will be minus 1 plus 5 by 2 and lambda 2 will be minus 1 minus 5 by 2. So, from here my lambda 1 is 2 and my lambda 2 is minus 3. So, after solving this one I can define my ycx from here, and this will be linearly independent. So, my ycx will be c1 e raised to power 2x plus c2 e raised to power minus 3x. So, my complementary solution is I am able to find. Now, the question is that how to find the particular solution. So, particular solution is this one. Now, I want to find my particular solution yx. So, in this case what is my FD? So, FD is my FD will be d square plus d minus 6. So, this is my FD. Now, if you want to find the particular solution ypx, this will be inverse of this operator into 5 e raised to power minus 3x. So, this one is there. Now, if you see that what will happen if I put f of minus 3, because this is minus 3 there. So, and I know that from here that lambda 2 is equal to minus 3 is the root of this equation. So, in this case this will be 0. So, what this is the case number 1, that my f of alpha is 0 and f derivative is not 0, because we have two distinct roots for this one. So, in this case f dash alpha is not equal to 0. So, from here I will write my FD. So, FD can be written as d plus 3 into d minus 2. So, I told you that if f alpha is the root of that one, then FD definitely can be written like this one. So, this is the factor which has become equal to 0 when putting d is equal to or alpha is equal to minus 3, and this is my gx. So, this is in the form d minus alpha into g of d. So, g of d, that g we have defined is the capital letter. So, g of d. So, my g of d is d minus 2. Now, I apply the operator method to find particular solution. So, in this case my ypx will be, so I can write this as d plus 3 d minus 2 inverse into 5 e raised to power minus 3x. So, I can define this as 5 d plus 3 and d minus 2 minus 1 e raised to power minus 3x. So, this one I want to apply. Now, this I know that this factor, this GD inverse is not equal to 0 when putting d is equal to minus 3. So, from here I can write as this value, and then it will become 1 over, so putting instead of d I am putting minus 3. So, it becomes minus 5 and e raised to power minus 3x. Okay. So, now from here I will get minus of, so this will cancel out, this is this one. So, it will be minus and then d plus 3 inverse e raised to power minus 3x into 1. Now, I will use my operator methods just we have done. So, I can take my e minus 3x on the left hand side and this will reduce to minus 3 to 1. So, it will be minus e raised to power minus 3x and this will cancel out. So, this will be d inverse into 1 and it can be written as minus. So, this is the integration. So, it will be x e raised to power minus 3x. So, this is my ypx. So, from here I can write my general solution as C1 e raised to power 2x plus C2 e raised to power minus 3x plus, so plus ypx. So, minus x e raised to power minus 3x. So, it is a e raised to power minus 3x also coming here. So, this can be reduced to this form plus C2 minus x e raised to power minus 3x. So, that is my general solution for this equation, where C1 and C2 are the arbitrary constants. Now, so this is the case we have just now solved. Now, I take the next one, case number 2, when my function f(x) on the right hand side is just a trigonometric function, some sin alpha x or cos alpha x like this one. So, what will happen in that case? Now, my f(x) in the previous case it was the exponential, but now we have a sin alpha x or cos alpha x. So, in this case what I will do is, what I will find what is the d f x. So, if I find out the d f x, so d of sin alpha x can be written as just taking the derivative. So, it will be alpha cos alpha x. Now, I am taking d square f x, then it becomes minus alpha square and then again sin alpha x. Now, what about d4 f x? So, it will be minus alpha square square then sin alpha x. So, now you see that if I take the derivative of this one sin alpha x or the cos alpha x, taking the first derivative you will get this value, but taking the second derivative I will get the same function back, but multiply by minus alpha square, and d raised to power 4 f x becomes minus alpha square raised to power 2 sin alpha x. So, similarly I can define that in this case if I take the even power of f x, so it will becomes minus alpha square power cube sin alpha x. So, like this one I can define all the even power of d to find out the derivative of that one. So, from here now suppose I have my differential operator that is defined in terms of f d square. So, f d square sin alpha x will become what? So, f d square sin alpha x become, if you see this one, if I take d square, then d square will be just minus alpha square sin alpha x. From here if you see d square sin alpha x becomes minus alpha square sin alpha x. So, instead of d square I am putting minus alpha square. Similarly, d4 f x becomes minus alpha square then whole square sin alpha x. So, f d square sin alpha x becoming f of minus alpha square, instead of d square I am putting minus alpha square sin of alpha x. Okay. So, now suppose I have my differential equation, my differential equation Ly in this form plus Cy is equal to sin alpha x, or Similarly, I can define for the cos alpha x. So, in that case my f d will be a d square plus b d plus c. So, this is my f d. Now, in the f d I have d square value only here, not here. So, what I will do that I want to find my particular solution. So, particular solution will be f of d inverse and into sine of alpha x. Now, from here I can show that from here my sine of alpha x can be written as f of d square inverse f of minus alpha square sine of alpha x. So, from here I can define this is a just a constant value. So, I can take this one on the left hand side and I will get sine of alpha x, and from here I can write that 1 of f minus alpha square sine of alpha x is equal to sine of alpha x, provided my f of minus alpha square is not equal to 0. So, that is the condition. So, from here, so what I will do is that now here it is a d square, but here we have the all the value d square is there, d is there. So, what we do is that instead of d square I will put the minus alpha square, and so from here what I will do is I can from here this can be written as f of minus alpha square d square into sine alpha x, or I can write here what I can write is that putting minus alpha square instead of d square in f d. So, whatever I will get, I will after that, after putting this one, I will get a function. So, that function will contain only new function. I can say that the g d inverse e raised sine alpha x. So, g d is that I can define here that g d is getting a new operator, it is a new operator, new differential operator after substituting minus alpha square in place of d square in f d. Okay. And then we will solve this one. So, let us take one example based on that one. So, let us do one example, then it will be more clear that how we can solve this one. So, let us take that I have a differential equation y double dash plus 2y dash is equal to sin x. So, let us do this one. So, in this case I want to find my solution. So, solution can be written as, so this is my equation. Now, I want to solve this one. So, my differential operator can be written as d square plus 2d y is equal to sin x. From here what I will do is that I want, now I know that how to find the complementary solution. Complementary solution I can find, but here my concern is to find the particular solution. So, I will define my ypx. So, ypx in this case will be, it will be d square plus 2d inverse sin x. Now, what we have done here, that now my alpha here is 1. So, what I do, I will put minus alpha minus 1 instead of, or in the place of d square. In the place of d square. So, what I will get? I will get here minus 1 plus 2d inverse sin x. Now, what will happen? You will, this is instead of d square I am putting minus 1. So, you will get, from here I can write 2d minus 1 inverse sin x. Now, how to solve this one? You can solve this one further. Then what we can do is that there is a trick to solve this. Generally what we will do is, the sin x I can write as imaginary part of e raised to power I x, because I know that e I x can be written as cos x plus I sin x. So, instead of sin x I can have this one. So, this is the imaginary part of 2d minus 1 e I x. Now, imaginary part, now this is what? So, this I have already done in the previous, that whenever the function fx on the right hand side is exponential, then what we do is that this become equal to 1 over, and in the d I am putting the I. So, it becomes 2i minus 1 into e I x. So, from here I get imaginary part of, so 2i minus 1. So, I simplify this one, 2i minus 1 multiply and divide by 2i plus 1 e I x. So, this can further be written as imaginary part of, so it becomes 2i plus 1, and from here you will get 2i square. So, it will be 4 I square minus 1 e raised to power I x, okay, because 2i is 4i square minus 1 this one. So, from here I can write as 2i plus 1 plus 1. So, I square is minus 1. So, it becomes minus 5 e I x. So, now I want to take the imaginary part of this. So, this will be, so this is the imaginary part. Now, imaginary part will be 2i plus 1. So, I can take this as a common, this one multiply by cos x plus I sin x. So, this will be. Now, I can take little bit further. So, this can be written as, so this is, so from here I will get 1 over minus 5. Now, 2I will multiply by cos, so I will get imaginary part, so it will get 2 cos x. Now, 2I multiply by this one, so that is real part. 1 is multiplied by the cos, that is the real part. 1 is multiplied by this one, is the sin x. So, this will be into sin x. So, this will be my ypx in this case. So, this is the way we can find out the solution. So, in this lecture we have developed the methods to find out the particular solution for the differential equation when the function on the right hand side is either the exponential form or the trigonometric form, that is the sin alpha x and the cos alpha x. So, in the next lecture we will deal with that when the function on the right hand side is some a polynomial. So, thanks for the watching this lecture. Thanks.